Well, finally, I wanted to show you a little something. Um, okay, concerning the derivatives and the partial derivatives and the general, some very general ideas. So here I have represented on GeoGebra the surface given by the equation z is equal to x squared plus y cube. Okay, so you see it's this nice surface. Of course, when x and y are positive, it's going to look a bit like a parabola, but when x, when y is negative, so it's going to go in the negative values. Okay, all right. So for this, I have in red here, you've got the point that belongs to this surface with coordinates, so 1 x equal to 1, y is equal to 1, and then it gives a z of 2. Okay, what would it mean to compute the partial derivative of this function at that point? Okay, so what I want to you to understand is what it means when I want to do this at some specific point, so xa, ya, right? And df over dy, xa, ya. All right, so let's go back to our drawing. It's going to be, you see, if I plot the plane of equation y is equal to 1, okay, so of course it crosses my point because my point is one point of the plane y is equal to 1, okay, so that's the one, right? You see what it means? So it cuts my surface, right? And where it cuts my surface, you see that the intersection between this plane and the surface that we had drawn previously is going to be a curve in 1D, right? It's going to correspond to equation. So let me find my notes. If I put y a is equal to 1, I've now got my function f of x1 is equal to x2 plus 1, okay? And that makes a function of one variable, g of x, all right? And what we see is the intersection of the plane and the surface we see is actually the graph of the function z, sorry, I can't seem to write, z is equal to g of x. All right, so well, I don't know why I lost my pen, but let's go back to the drawing. Right, so the line that is at the intersection is the one where y is fixed at the value 1, and this this curve, of course, is going to have a derivative, and well, we can compute the derivative of that curve, and it has it's going to indicate the slope of the tangent at the point A, okay, and this is going to be given by df over dx, right? You see, if you compute the df over dx at the point x, y is equal at the point A, with a fixed value of y, you're going to get the slope of the tangent. Okay, so that's it. And of course, if you want to do also, on the other hand, df over dy, so we should have y that moves, and at that point, so around that point, so that's going to be for a fixed value of x equal to 1. So what does it correspond to? So it's no more the intersection with the plane of equation y is equal to 1, it's going to be the intersection with the plane x is equal to 1. Okay, so that gives you the curve you see at the at the boundary between the surface in blue and the plane in orange, right? So again, if you compute the slope of the curve you obtain, it corresponds to the partial derivative in x. In yes, no, sorry, in y. In y at for x fixed value of x is equal to 1. Okay, so what else did I want to show you? Oh yeah, once you've got the two partial derivatives, you can compute the tangent plane. So we have a nice tangent plane here. We can see it here. So tangent plane, of course, equation being z is equal to value of the function plus value of the first derivative times x minus the xa plus value of the partial derivative according to y times y minus the ya, right? What else I want to show you? Oh, okay. Next thing I have, this is the plane of equation y is equal to x. And again, if you look at the intersection between that plane and the curve, what does it correspond to? Well, let's have a look. If it just corresponds to the fact that I put y is equal to x. So what I'm creating, the curve that I obtain at the intersection, is going to be something where f of xx is equal to what? A new function. So, and that's, sorry, and what we see at the intersection is the graph of the curve z is equal to h of x projected on the plane of equation y is equal to x. You see the intersection. Well, actually, it goes again through the point of coordinates 1 and 1 because it happens to belong to the plane. And if I do want to find the derivative of that curve, the slope of the tangent of that one-dimensional curve, well, that would correspond to the derivative according to x of h of x, which is the derivative according to the straight derivative according to x of whatever is going to be to bear the name x in the expression of fxx, which it would just be d over dx of x2 plus x3. Okay, if I plug in the expression of f also the value of x for y, this is the expression that I get, okay? And if you compute this derivative, of course 2x plus 3x squared, of course it's going to be very, very different from the partial derivative of f according to its first variable, which is just 2x, right? Right, okay. And finally, one last thing that I wanted to show you, so that was when we had this, when we plug x for the both variable, and you can find again these values by using the chain rule, by the way, right? Now, the last thing that I wanted to show you is what if we look at the intersection with a more complicated surface than just a plane. Here the cylinder we obtain is actually just the unit circle, all right? And then we will reproduce this unit circle up to all altitudes. And so it does intersect my surface because every point of this unit circle has an image on the curve. And so this is something that we could describe as, so sorry about that, points of my unit circle can be described as x of t is equal to cosine of t, y of t is equal to the sine of t, and so I would be able to create a new function, I don't know whichever name, f tilde of t, which would be f of cosine of t for the x, y of t for the y. Okay, and so that's a one variable function. If you could plot it in a rotating frame, what it would give you is, you see the nice curve we obtain at the intersection of this cylinder and our original surface, right? And if you think in terms of partial derivatives or of derivative, if you want to compute the f prime of t, which again, let me go back to the drawing, corresponds to the curve that is at the intersection of the orange areas and blue areas. it's it's really a one-dimensional curve. You can plot its slope at each point. You can compute its slope at each point. It's the derivative in t of our function. So that would be given by f prime of t, and that would be given by the derivative of the f of cosine of t y of t, which of course you can compute because, sorry, y of t being the sinus of t, okay? And of course you can compute that using the chain rule as usual, okay? I hope that was maybe clarifying some points you may still be struggling with. Okay, so don't hesitate to ask questions. Okay, thank you very much. See you very soon. Bye.